Assignment is solve the circuit right here. So what I want y'all to solve for, you can solve for VB, solve for IB, you can solve for IC, we need to solve for VC, let's go ahead and solve for VRC. Beta of the transistor is 100. This will work out, guys. I checked. So VB, IC, IB, IC, VC, and VRC, and then VCE, which tells us what region the transistor is operating in. VRB. And that would be the base resistor. I'll give you VB. VB is 0.7 volts. So what's VRB going to be? Huh? 4.3. What do you lost on? I mean, it's a series. It's a low. We know that as soon as we know this guy right here drops 0.7 of a volt is forward bias, and this is a loop. According to Kirchhoff's law, the sums of the voltage drops have to equal to that right there. So if this guy right here is dropping 0.7 of a volt, then that guy right there is going to drop 4.3 according to Kirchhoff's law, right? You understand that? And we even did that in diode circuits. So every time we went through a forward bias diode, we took off 0.7 of a volt. We're doing the same thing here. Except on a diode was going the opposite way. On the diode we subtract the diode drop is on the front end. Here the diode drop is on the rear end, right? So what would IB be? What's that? 430 microamps? So what's IC going to be? Huh? 43 milliamps? Oops. Okay. We multiplied IB times beta. So that's the only new formula. All it is a gain. It's a gain formula, right? You understand that? And what we're going to have to get used to in transistors is we're going to always have a gain. If we don't have a gain, you shoot the engineer. I used this formula we just got through before. I said IC is equal to beta times IB. It's the formula we did, right? No, you calculated IB as this. I gave you beta right there. I gave you the beta of the transistor right there. No, 430 microamps. So IB is 430 microamps. So IC would be equal to 430 microamps times 100. And of course, when we do that, we get 43 milliamps. So how much voltage is going to be dropped across RC? So what we did is we just calculated the collector current, or roughly the collector current. We know the emitter current's going to be a little more, but we don't care about that now because that resistor is not in the emitter in the first place. So what would VRC equal to? I know the size of RC and I know the current flow through RC. There's a current flow through RC. I know so what's it going to drop? Okay, it's going to drop 4.3 volts. So what's VC going to be? If I measure across VC, what's it going to measure? What's that? What's that? How can... Okay, we got two elements in this. We got two elements in this loop right here. Of course, the Kirchhoff's current voltage law. So we're not going across a p-n junction. We're going across a transistor. That is not a p-n junction. According to Kirchhoff's voltage law, the sums of the voltages in a series loop have to equal to the applied voltage. This guy right here is dropping 4.3 volts. I got 10 volts applied to it. This guy's dropping 4.3. How much is the transistor dropping? Huh? Well, 4.3 plus 4.3, that's 8.6. I got to drop 10 volts. I got to drop 10 volts in it. 5.7. I mean, if I would have came up and if I would have drew this circuit like this, right? And if I was to put that as a rheostat right there, and I said I'm putting 10 volts right there, this guy right here is dropping 4.3 volts. How much voltage drop across the rheostat? Everybody would have said what? 5.7 volts. But for some reason, you can't picture the diode as that transistor as being a rheostat. That's all it is. It's just a rheostat that we're controlling electronically. So what I've done is I've adjusted my rheostat to make that with this base current. I've adjusted this rheostat to drop 4.7 volts. 5.7 volts. But we didn't know that. All we knew was we could calculate collector current, right? Collector current gave me the voltage drop across that resistor. If I know the voltage drop across that resistor, Kirchhoff's voltage law says the sums of the voltage drops in a series loop. So here's the series loop right here. It says the sums of the voltage drops have to equal to the applied voltage. So if this guy's right here is dropping 4.3, then the transistor itself has got to be dropping what? 5.7. Is it saturated? So my voltage collector to emitter would be, if I measure from here to here, right now we measure 5.7 volts. Is it saturated? Yes or no? Is it dropping less than volts? No, it's not less than volts. It's dropping 5.7 volts. It's not saturated. Is it cut off? Well, if it was cut off, it would be dropping 10 volts. Is it dropping 10 volts? No, it's dropping 5.7. So it's not cut off, right? So where's it at? It's operated in the active region. And that's what's very important about that voltage collector to emitter. We can tell right off the bat what region that transistor is operating. So if it's operating in saturation and it's supposed to be operating in the active region, then we can figure out what the problem is real fast. So a lot of times to troubleshoot a transistor, if we know what these bias voltages are supposed to be, then if they're not what they're supposed to be, then something's wrong. And then from those measurements, believe it or not, it's not very complicated to figure out what's going on. So VRC was going to equal to 4.3 volts, and VCE would be equal to VC. And here, VCC and VCE and VC would be equal to the same because the emitter is connected directly to common. So a while ago, that was a poorly designed circuit. This was a pretty good designed circuit. Are we okay? What law did we use? Well, there's only one new law we learned, and that was a formula for gain. So if we know that the beta is equal to IC over IB, if I know two of these things, I can solve for the other, right? You understand? So what did we know here? We knew the beta, and we knew the base current. The base current was real easy to calculate because all we had to do is calculate voltage drop across that resistor right there. That's real easy to calculate. What law did we use? We used Kirchhoff's law. This guy right here is dropping 0.7 of a volt. So what is that guy right here? So this is the series loop right there. Kirchhoff's current law, voltage law says the sums of a series loop has to equal to the applied voltage. Has to. Not maybe, it has to, right? So if this guy right here is dropping 4.7 volts, then this guy right here has to be dropping what? 4.3. So what did we do with that 4.3 volts? We calculated the base current, because now I know two things. I know the size of the resistor, and I know the voltage drop across the resistor. Well, that dang resistor is in series with the base. So if it's in series with the base, whatever current flowing through that resistor is the base current, right? Y'all understand that? Okay, so now what do I need to do? Well, I need to get from this side of my transistor over to this side. Well, what's going to get us from this side over to that side? The beta. If I know the beta and I know the base current, then what can I calculate? If I know the beta and I know the base current, what unknown do we have? We don't know IC, right? You understand? So we can solve for IC. So if I know this formula, then I can come up here and develop my equation thing, where I say beta is equal to IC over IB, and I just cover up what I want to solve for. What do I want to solve for? IC. So what's IC equal to? It's going to be equal to beta times IB. Now, where did y'all learn all these rules at? Where did y'all learn how to do the three expression thing? Where did you learn that at? Ohm's law. You do Ohm's law and Watt's law. We throw those things over there we're teaching hydraulics, pneumatics, and we have a bunch of three expression equations in that. We just throw it in these little things like this, and we can solve for whatever we want to without even knowing algebra, right? So this guy right here, this is nothing but a gain. That's all it is. It's the ratio of IC over IB. And then if we know this ratio, if I know IC, I could solve for the IB that's required to get that. If I know the IB, then I can solve the IC that's required that we obtain from that IB. So we took that 430 microamps, we multiplied it times the beta, because IC is equal to beta times IB, multiply that, and that gave us our collector current. So now I know my collector current. I know the size of that resistor, I know my collector current. So what can I do now? I can solve for the voltage drop across that resistor right there, right? You understand? Okay, I know the voltage drop across that resistor right there. I know this is another series loop right here. If I know that guy's right there is dropping 4.3 volts, then this guy right here has got to be dropping what? 5.7. And then when we take that, we can figure out what region the transistor's operating. But we're still using two batteries. And we're going to do this with our trainer. The problem with our trainer is we can't use the two power supplies on our trainer, because the power supplies, the variable power supplies on our trainer are hooked up like this. I'm sorry, I've got them connected to common. I made a mistake there. So this is a terminal. This would be labeled, this is a terminal. It would be labeled plus. This is a terminal. It would be labeled minus. And this right here is ground. See, we can't use this for this power, for this circuit, because here both negatives are connected to what? Ground. So what are we going to do? So I can't use the power supplies on the trainer. So what are we going to have to do? What? we'll have to use an external power supply. We'll use one of these right here. This like that I use. We can't use the two variable power supply on this that's connected the same way. But what we can do is we can use one of these power supplies, one of the trainer's power supplies, connect the commons together, right? And then we can use that. So you can't, when we hook up this circuit, so this is one of the circuits we're going to use. But pretty soon we're going to move into a single power supply bias situation. Okay, the next thing they talk about, and we'll just, I know it's almost time to go, is the next thing they cover in the book is these things called collector characteristic curves. And believe it or not, they don't give them to you anymore. Some data sheets still contain them in there. But what we can do is we can come up with a pretty good approximation of them just with the beta of the transistor. So what they do is, once the transistor cuts on, so down here on this line, this is voltage collector to emitter. Then this line right here, this is the collector current. And then this right here would be the base current. So that would be the base current you'd have. And what they would do is they would have different base currents. So what they'll do is they'd come up here and they'd set the voltage to a certain thing. And then what we do is we start applying a base current until it starts leveling off, and then we have the ability to adjust the voltage base to collector, and it doesn't change the collector current. Now it's going to change it a little bit because of the resistance of the transistor. So notice these lines are not flat across, they have a slight slant to them. So even on our diode, so if you can take the diode characteristic curve and come over here, this is basically the same curve. But now instead of putting it vertical like that, we're laying it on its side. So what we can do at different base currents, we're going to get a certain collector current, even though the collector to emitter voltage varies, which is a really neat feature, because the collector current is not, as long as we don't break it over. So if I get my voltage up too high, if I get my voltage collector to emitter too high, then it's going to break over, right? If I don't get, this would be cut off, and this right here is bad right here. This would be what we call the breakover voltage. But as long as I'm between when the transistor starts cutting on and the transistor breaks over, then the collector current is controlled by what? The base current. It's not controlled by the voltage across the transistor. It's controlled by the base current. So what that means is we can use a collector resistor and use it to vary an output voltage for a certain current, right? Y'all understand what I'm saying? Which is really, really neat. So the collector to emitter voltage does not set the collector current. What sets the collector current? What current sets the collector current? The base current. The base current sets it, right? And then what we can do once we get that is we can figure out where we want to operate our voltage at. So here, if this is voltage to collector emitter, this would be saturation. Up here, this would be cutoff. And then what I would do is I would take this current right here, and I would draw a line to this guy right here. And then what we'd want to do is we would want to operate our circuit right there. And we call this the Q point of the circuit, the quiescent point. And if we can operate it at that region right there, if we're going to operate it as an amplifier, then we could move it toward cutoff and saturation, and it still wouldn't affect the collector current, right? Does that make sense? Now these, we're not going to use these as much. Like I said, they don't give us these much. We can get a rough feeling on it by using the beta of the transistor, but if we do that, our lines would be straight across. But using a line that's straight across is not going to give us a big problem because it's only got a slight slant anyway, right? You understand? So this is why they don't give you collector characteristics first. We used to have what they call a curve tracer. I wish I could find it. So what you could do is you could set a transistor in there, and you could hook up an oscilloscope to the output. You could hook it up to the base and the collector, and it would generate these curves for any transistor you wanted to. It was a really neat piece of equipment, but I haven't seen it since I've been. So what we'll do next class is we'll work with saturated switches. We'll figure out how to set up a saturated switch. Say, oh, that's neat. I'm gonna go home and do something. And then you can look like that video Brian showed. Send me that link on email. I'll put that on the platform. This is the guy. It looks like he needs to get out of the business. Y'all really enjoy it. Kind of like what's his name? Studio C. They're all Studio C. Those are all staged. You ought to watch some of those videos. We used to show those in class. But they got Sterling. What's his name? Something Sterling. It's so funny. I'll show y'all some of those. Yes, I think there's one inside that. I don't know where my dustpan. Somebody stole my broom in my dustpan. From here. Charles, did you get 5 questions? I can give you credit for the 5 questions, but I can't give you credit for asking. So we did that before you got here. But that's worth half credit anyway. Just the questions is worth half credit. I don't need them. I just need to see.
Oh.
Yeah, so what you did is everybody asked their question, or 3 of the questions in class. So I can give you questions, I give you credit for the questions, but I can't give you credit for.
Those want me to okay.
No, can't do that. Okay, so you need to make every effort to get here on time, right?
My job.
You okay? I don't blame you. I can tell you don't feel good.